Hello physics students, this is Dr. Brenzy here, and this is lesson 2.2.3. And this lesson is on friction. We've already discussed friction at some level, but I want to give to you an important relationship between friction force and normal force. So at a microscopic level, we know that friction occurs when two surfaces interact by rubbing against one another along the surface. At a macroscopic level, what we know is that the friction force is actually proportional to the normal force. What that means is that if we were to press down on this block with a force, we know that according to Newton's third law that the table will exert a force back up because the normal force has to balance the force that we apply down along with the weight of the block. So the normal force is going to increase. Now imagine pressing down on that block and then trying to move that block also along this surface here. Would you expect it to be harder or easier when you're pressing down on this block to move it along a rough surface? Well, hopefully your personal experience tells you that it's harder. And the reason it's harder is because friction force is proportional to the normal force. Another way we can say this is that the force due to friction is equal to a constant times the normal force. Okay. This constant, which is given as a symbol mu sub k, mu is a Greek letter. Mu sub k is what is called the coefficient of kinetic friction, and it is a unitless constant. So unlike acceleration due to gravity, which has units of meters per second squared, this is a constant that has no units attached to it. Now friction also works when the object is at rest. And the way that works is that it will match any applied force in the horizontal direction until it reaches a maximum friction force. So if I apply a really small force in this direction, the friction will match that force up until a certain point. And it will match it so that the block initially doesn't move. So it takes at least a minimum amount of force to overcome the force due to friction when the block is at rest. So when a block is at rest, we can say that the force due to friction has to be less than or equal to this coefficient, which we call the coefficient of static friction, mu sub s, times the normal force. So, when we have an object at rest, we know that the friction force is actually less than or equal to mu sub s times the normal force. And when an object is moving, the friction force is equal to a different constant, mu sub k, times the normal force. Now these coefficients of friction, mu sub k and mu sub s, are not equal. I mean, if they were equal, why would we bother using two of them, right? Why wouldn't we just use one and call it mu? Well, experience has told us that these are not equal. Now which one of these do you think is greater, and why? Take a moment to stop and jot this on maybe right underneath your notes here, and give your guess, and then we'll continue the video as soon as you're done with that. Okay, hopefully you had a moment to stop and jot what your answer to these two questions is. Now I'm going to go into some detail about figuring out which of these is greater. And if you're in my advanced class, Or, well, if you're in my advanced class, you don't need to necessarily worry about all this math unless you really want to. But there will be a moment you can skip ahead, and I'll put that in the notes, so that you can kind of skip over this stop and jot explanation, and I can go and just give you the straight answer. But for those of you in AP, I want you to understand this argument, so stick around. And those of you in advanced physics who are curious, you can stick around too, although it will involve a little bit of calculus, but I think it's calculus that I should be able to explain pretty easily. Okay, so let's do a little thought experiment. So this is like an experiment that we would do in our mind here. So when an object is at rest, we know that the force due to friction has to be less than or equal to, and let me erase this guy right here. It's in the wrong place. We know that it has to be less than or equal to this coefficient of static friction times the normal force. So in order to move an object, I have to use a force that is a little bit greater than this maximum force, mu sub s times the normal force. So why don't I apply a force that is equal to that maximum static friction force plus a little bit more. And in math we can say, or in physics we can say a little bit more by using this symbol, which is the small letter delta. So the small delta F, an additional small force. Okay, the reason that we use small delta is to remind us that it's a small change, unlike the delta you're used to. This delta, which is a capital delta, that is a big change. We just want a small change, so we're going to a small delta. And you're going to see that a lot in physics, so especially if you go into college physics. All right. So we're applying a force to move this block to the right that is slightly greater than this maximum static friction force. Well, once we do that, the object is now in motion. And when the object is in motion, our friction force instantly changes to be mu sub k times F sub n, or the coefficient of kinetic friction times the normal force. As soon as that object is in motion, we have to change the friction force. So the net force on this block is equal to the force that I just applied minus mu sub k times the normal force. Okay. Now, I already have an expression for the force that I just applied. It was just a little bit more than the force I needed to overcome static friction. So we're going to replace F sub A with that expression, and we get that right here. Okay. And when I do a little bit of algebra, I'm just going to gather up all my F sub n terms together. And when I do that, I get mu sub s minus mu sub k times the normal force plus a little bit more force than that. So that would be my net force on the object. Okay, let's continue our thought experiment. Now, delta F, this little delta F can be as small as we'd like to make it. So let's take the limit of this little delta F as it goes to 0. So the net force, basically what I'm doing here, I forgot to write this down here, I'm taking the limit as little delta F goes to 0 of our net force. Okay. So this limit as delta F goes to 0, so as this gets closer and closer to 0, F net gets closer and closer to this expression right here. Mu sub s minus mu sub k times our friction, or our normal force, excuse me. Okay. Oops. A little extra dots there. Let's see here. Oops. Oh, I didn't write the rest of this. Okay. There is a slide that I'm missing. Let me see if I can put it in real quick. Actually, I'd have to pause the video. Well, okay, so now we have two possibilities here. If mu sub s is greater than mu sub k, then we know that this net force right after we get the object moving is a positive number, right? Because the normal force is going to be positive. The net force is also going to be positive. Okay? So we applied a force in this direction, and immediately as soon as we started it in motion, we ended up with an F net right away. That is a positive number. Okay. So let's think about that. Okay, so if I have a block that initially starts at rest and I'm overcoming friction, what that means is that as soon as I start it in motion, it becomes easier to move because I've instantly gained an F net. Okay. Well, let's think about that. If you and your friends were moving a big refrigerator and trying to slide it across the floor, you push on it pretty hard to get it going, right? But once it gets going, it feels easier to move, right? Because you've instantly gained a net force in this direction, and then you don't have to apply as much force once you get it moving. But let's think about the other case. What if mu sub k were greater than mu sub s? Well, that means that our net force would be less than 0, which means if I applied a force to the right, as soon as I got it moving, my net force would move it to the left. That's nonsense. So we definitely know that this case is nonsense. Okay? So it has to be true that your coefficient of static friction is greater than your coefficient of kinetic friction. All right. Oh, and I have a bunch of stuff here I have to erase. All right, so for all possible surfaces, and now you're returning to your notes, by the way. For all possible surfaces, we now understand that it has to be true that the coefficient of static friction has to be greater than the coefficient of kinetic friction. Okay? So I think I already gave you the consequence of this being true, and that is that on a surface with friction, it's harder to push against friction to get an object going into motion than it is to keep it in motion. So if we have this big fridge that we're trying to slide across the floor, okay, you have to apply more force to get it going than you do to keep it going. So once it gets going, it's easier to push. You don't need to apply as much force to overcome the friction force, because then the friction force is equal to mu k times the normal force. That is the force it's resisting, pushing back. Whereas here, we have a bigger force pushing back, mu static times the normal force. So it's a larger force that you have to overcome in order to set it into motion. Okay, so those are the notes for today for lesson 2.2.3, and we can apply this in lots of different situations. There will be situations where you're given the normal force and you're given like the force of friction or the net force, and you have to find either this coefficient of kinetic friction or you have to find the coefficient of static friction. So there are lots of applications to this, so now we're going to start building this into some of our other problems. Any problem that involves friction, now we can say, well, the coefficient of kinetic friction equals 0.1 or something like that. And then you'll use that times the normal force to figure out what the friction force is. All right, that's it for the notes for now. And I look forward to seeing you in class tomorrow, and we'll get an opportunity to practice some problems involving coefficients of static and kinetic friction. All right, see you then.